Very good evening, everyone, and welcome to the Amateur Radio General Class, session number 4. Our previous class, we went into some questions in the question pool, so we did a question pool review. We also looked at Kirchhoff's current law. We dealt with alternating current values such as the peak to peak, and root mean square or RMS. We also looked at a worked example for RMS calculation. We looked at a worked example for peak to peak. We did the power formula for both AC and DC circuits. We had a worked example or a few worked examples in respect of power. We also tackled the concept of PEP or peak envelope power, and we also did an example or worked example on PEP. So let's see, where are we in our curriculum? So we are still in very early days yet, and we are currently on the section called Electrical Principles. Just a reminder that you can take practice exams, and these are the URLs or the links to take those practice exams. And we have been getting some pretty good feedback from persons who have chosen to take those practice exams. Some people are saying that they're quite surprised as to how well they're doing. And indeed, I'd like to encourage you to consider taking the exams, even at this early stage. You certainly have the capability. So we did have an error on a particular slide last week and made a correction. What is happening is the software I'm using, for some reason or the other, subscripts and superscripts sometimes get reverted. It's not very clear why. It still is happening. However, I'm trying to do everything possible so that it doesn't manifest in the presentation. So if we to look at this slide, the error was instead of 0.007 squared, the slide had 0.0072, which was incorrect. So I hope that didn't confuse anyone. It was 0.007 squared. When you square that, you get 0.00049. So that's the corrected slide. It is also corrected in the slide deck that you would have received earlier in the week. All of those slides were corrected. So we had a couple of questions, some of which were very common. So let's deal with the questions, the Q&A one time. So the first question that we had, and it was a very popular question, why is 0.707 called the magic number? Well, first of all, let me admit, I am choosing to call it the magic number. It's not somehow universally called the magic number, right? So let me admit that first of all. But you know, sometimes we have numbers and it's very useful that we anchor to a number. So I just choose to call it the magic number 707, all right? So 0.707 is the magic number according to the instructor. But what is it really? It's the reciprocal of the square root of the number 2. And it is indeed the value that is used to convert from peak value to the RMS value. So that's what we use that magic number for. And it is very useful when we are comparing AC and DC values. And we'll discuss just in a minute in the second question a bit more on that comparison between AC and DC values. So also we have it there, how you get that number 0.707, it's 1 over the square root of the number 2, or as we say, 1 over root 2, or the reciprocal of root 2. All right, so I hope that helps a bit. The second question, which is also related in a way to the first question, takes us a little deeper. Why are RMS values used instead of peak values for AC voltages? Why do we use it? What's the importance of it? Well, first of all, we give AC voltages and currents, by the way, as RMS values because it allows us to compare, or as we say, sensible comparison to be made between a steady DC voltage and the AC voltage. So the steady DC voltage, for example, could come from a battery. So here's how I tend to look at it. So let me pick on a couple of students in the class. So let us say Sylvester is a sort of AC kind of guy, and Sylvester is peeling oranges. So Sylvester may start off peeling oranges at 1 every minute or so, and then he might ramp up a little faster. In a couple of minutes, he might be up to peeling 4 oranges per minute. And then probably a little later on, in the next 10 minutes, he's up to peeling 6 oranges per minute. And then, you know, he starts to back off a little bit and goes back down to 4 oranges per minute peeling. And then maybe he stops peeling any at all, and so on. But let us say we have another student in class, let's say Marissa, who she's pretty steady. So she starts off peeling oranges, and she starts off peeling maybe 6 oranges per minute. And every minute that goes by, she's peeling 6 oranges. Now, at the end of the day, or at the end of 1 hour, Marissa may have peeled 100 oranges. But guess what? Sylvester, who is a sort of AC guy, you know, he's up and down, could also peel the same 100 oranges within that hour, right? So if you're comparing both Marissa, who is a DC sort of person, you know, very steady as she goes, she peels 100 oranges in an hour, just she does, 6 per minute or whatever the figure is. I haven't worked out a number, but she's steady, she's keeping to one value. And at the end of the minute, or at the end of the hour, she has peeled 100 oranges. But Sylvester has done the same thing. He has done the same amount of work, except that he's just not steady. He varies how quickly he peels at 1 minute, and next minute he peels a little slowly, and so on and so on. So to compare both Marissa and Sylvester, they have both peeled 100 oranges within the hour. So in a sense, although Marissa is DC and Sylvester is AC, both of them have peeled 100 oranges within the hour. So if we were to go back to the question about why we use RMS values, sometimes we want to compare a DC voltage to an AC voltage so that we could understand for a particular given AC voltage, what would be the DC equivalent. And towards the right-hand side, just put up a little graph there to show us in our house current. Our current in Trinidad and Tobago, TNTech is the supplier. We have students from different parts of the world. So whoever your power company is will supply a particular voltage. So if you are getting 120 volts AC supply, when the power company tells you it's 120 volts or 220 or 240 or 115 or 415, whatever voltage you get, that voltage is the RMS voltage that they're telling you about. But if we were to look at this graph on the right-hand side of the screen, we will notice that even though it's 120 volts RMS, you'll see this is the RMS line here. 120 volts RMS, you'll see the peak is much higher. You'll see it's actually closer to 170 volts. So the peak here is about 170 volts, but you don't say that you have a 170 volt peak power supply coming from your power company. You say you have a 120 volt supply. You leave out the word, you leave out the term RMS, but it is actually RMS that you mean, or the RMS is silent. So when we're giving voltages and currents, and we will come to that in the next question, when we're talking about AC power, we are giving the RMS, or the root mean square value. It is the DC equivalent. It's the equivalent that will cause the same heating effect for an AC voltage as equivalent to a DC voltage. All right, so I hope that helps a little bit conceptualizing this graph. Maybe people thought when we said 120 volts AC from the plug, the receptacle outlet in your wall, that was peak. No, that is actually RMS. The peak of that voltage actually goes much higher to 170 volts. That's why the insulation also needs to be able to handle a higher voltage than the voltage that you're saying. You're saying 120 volts, but you see the peak here is 170 volts and so on. So the last question, question number 3, is also related. So the question is, when given current and voltage for an AC circuit to find power, does one assume that the current is RMS current or IRMS? Actually, I found that to be an excellent question. And the simple answer to that is yes. When we are doing power formulae and we are using V and I and so on inside of there, it is the RMS voltage and the RMS current. So you're quite correct, the student, in asking that question. I guess you anticipated it was, hence the question. So very good extrapolation of thought, and that shows, pretty good understanding, I must say. So congrats to the student for asking that really excellent question. And we just reproduced the two power formulae on the screen here. So you can see it's RMS voltage. So this is V squared, but it's RMS voltage squared. This is I squared. It's RMS current that you're squaring, right? So very good questions indeed. Okay, so what we will do at this time is we will do or tackle some of the questions in the question pool. Seeing that we covered quite a bit of the theory last class, we are going to basically run through very quickly the questions in the question pool related to last class slide deck. So let's put those questions up. All right. So the first question, how does the total current relate to the individual currents in each branch of a purely resistive parallel circuit? So we will dissect that question a little bit, but before doing so, I'd just like to remind all of the participants that next to every question in the no nonsense guide, which is what we're using, there's a number, and this number relates to the question pool number. So we circulated the entire question pool to all of the students that has the question, the right answer, and also the distractors, the three distractors or the wrong answers. And if you would like to refer this question back to the question pool so you can see what the wrong answers are, just simply look for the number here and you could look at the question pool for that number. If you're looking at it on your computer on a PDF, you just hit Control F, Control Find, and you type in this number and it will take you straight to that question. So you can see it quite efficiently and see what are some of the wrong answers or the incorrect answers or the distractor answers. So in dissecting this question, they're asking us about the total current and how does it relate to the individual current. And what type of circuit are they talking about? We're talking about a parallel circuit. So last class we learned that in terms of the current flowing in a parallel circuit, the sum of each of the individual currents gives you the total current. You just add them together. So that is the answer. It equals the sum of the currents through each of the branches. Yeah. Okay, so we're going straight ahead. Next question. What value of an AC signal produces the same power dissipation in a resistor as a DC voltage of the same value? Well, we covered it last class, and we also talked about it during the Q&A today. But let's dissect the question still so that we could take out the mystery to the question. What are they asking us? The value of an AC signal that produces the same power dissipation. Right, so those are the key words here so far, but they're asking us as a DC voltage of the same value. So if you have a DC voltage and you want to know what AC voltage will allow for the same amount of power dissipation, you have to convert that using the RMS value or the RMS formula. So the answer to that question is RMS. So I'm hoping that you're seeing the application of the theory in terms of the question in the question pool is for each of us to get a surface understanding at least of the theory so that we can deal with these questions and not just have to remember the answer, but we have a little idea of why the answer is the correct answer. Next question in the question pool. What is the RMS voltage of a sine wave with a value of 17 volts peak? So let's dissect that question also. What are they asking us for? They are asking us to find the RMS voltage. And they tie us up a little bit here, right? They say have a sine wave. They didn't tell us an AC, they didn't tell us AC or alternating current. They say a sine wave. But we know an alternating current, right? In AC, it is a sine wave. This wave that you see on your screen, when you see a wave that looks like that, that is called a sine wave or a sinusoidal wave. And they put that into the question to try to trick you, but we are not tricked easily, are we? They want to know what is the RMS voltage. And remember, we said when we talking about RMS voltage, quite often, well, we are in fact referring to AC or alternating current. They're just tricking us here by telling us about a sine wave. But guess what? We learned what a sine wave is as a result of the question. So they're asking us about the RMS voltage of an AC current when the peak is 17 volts. And last class, we learned about the formula for converting from a peak voltage to an RMS voltage. And we simply have to multiply by what? Our magic number. Yes. So we did this as a worked example in the last class, and we got the answer of 12 volts. The workings is here a little bit, so it's just a little more, cryptic in terms of they're presented to you, but we did this in the last class. So if any doubts as to how we got 12, please refer to the slides from last class. Okay, next question in the question pool. What is the peak-to-peak voltage of a sine wave with an RMS voltage of 120 volts? Okay, so they're trying to tie us up here again and telling us about a sine wave. But we know a sine wave simply means alternating current in our context. The other clue is that we're talking about RMS. Yeah, so it has to be alternating, right? So what are we to solve? What is the question? What is the peak-to-peak voltage? Now notice they didn't ask us about the peak voltage. They asked us about the peak-to-peak voltage, right? And remember, the peak-to-peak voltage is twice the peak voltage, yeah? So again, we did this exact question in the slide deck last class. And they're asking us for the RMS voltage is 120. What is the peak-to-peak? And we did that question last week, and we came up with the answer of 339.4 volts. And it was simply multiplying 2 by 1.414 multiplied by the voltage. So just refer to this slide if you are in doubt as to how we got this. So we're just barreling through these questions. We covered all of this in the last class. Next question. How many watts of electrical power are used if 400 volts DC is supplied to an 800 ohm load? Again, another question we did as a worked example. So we use the power formula. That's what they're asking us. How many watts? So we have to use the power formula. But which of the power formula should we use? Well, what did they give us? They gave us the voltage and they give us the resistance, or the 800 ohm load, I should say. So we know we have to use a formula that involves voltage, or V, and R, resistance. So we use the power formula, P is equal to V squared over R. So when we apply that formula, we work that out to 200 watts. And again, we did the same question in the slide deck last week. You can always review where we did it step by step. Next question. How many watts of electrical power are used by a 12 volts DC light bulb that draws 0.2 amperes? So let's dissect that question a little bit also. What are they asking? How many watts? So we know once they ask us watts, we know we're talking power, because the unit of power that we have learned is called the watt. So when they say how many watts, you translate that to what is the power. So you need a formula for power. Power equals something. But what did they give us? Because we have to use a formula based on the values that they have given to us in the question. So they want to find out power in watts. But what did they give us? They told us it's a 12 volt DC light bulb. So they give us voltage, 12 volts DC. And what else did they give us? They say 0.2 amperes or 0.2 amps. So they gave us voltage. And what is amperes? That's current. So they gave us voltage and current, and we want to find out power in watts. So we need a power formula that says power is equal to something in terms of voltage and current. And we know that power formula is P is equal to V multiplied by I. So we apply that formula, and we end up with 2.4 watts. Again, this was a worked example in last class. Please review if it's not clear how we got from the question to the answer. Next question, moving right along. How many watts are dissipated when a current of 7.0 milliamperes flows through a 1250 ohm resistance? Okay, let's dissect that question. You probably already have guessed. Just like the previous question, what are they asking us? They're asking us how many watts. Again, when they ask us about watts, what are they asking us? They're asking us about power. So we know yet again, we need a power formula. Power is equal to something. But what did they give us? Which formula should we use? Let's see what they have provided to us. They have provided to us the current, 7 milliamperes. what have they also given us? They have given us resistance, 1250 ohms. So they have given us I, which is current, and they have given us R, which is resistance. And which power formula do we know power is equal to something that has I and R? Well, we learned it's P is equal to I squared R, or I squared RMS R. And we apply that formula, we drop these values inside of the formula, and we end up with 61 milliwatts approximately. Again, another worked example in the slide deck from last class. We took it step by step. Let's go again. Next question in the question pool. What would be the RMS voltage across a 50 ohm dummy load dissipating 1200 watts? Well, look how they're trying to tie us up. Look at all the extra information that they give us. They're talking about dummy load and so on. But let's see, what are they asking us? They are basically asking us for the RMS voltage. So we have to use a formula that has the RMS voltage in it. What else did they give us? They tell us it's 50 ohms. So we know that formula has to have the term R in it because R is resistance, R is ohms. And they gave us power, which is 1200 watts. Watts, once they tell you something watts, you know that is power. So we need a formula that has P for power, V for voltage, and R for the load, or the 50 ohms. And when we apply that formula and algebraically manipulate it, we plug those values in and we solve and we get 245 volts. Again, completely solved in the previous class slide deck. So if you want to know how did we get from here to here, please review the last slide, which works it out step by step, or as we say in primary school, we showed the working. All right. Okay, so let's go to another question in the question pool that talks about PEP. So last class, we had a couple of graphs or oscilloscope graphs on the screen, and that's why we did those graphs, to be able to answer these types of questions. What is the ratio of peak envelope power to average power for an unmodulated carrier? So if you recall from the last class, the unmodulated carrier, you saw it was a steady state. It was maximum at all the time. And when you have a signal that's maximum all the time, the average is actually the maximum. So therefore, the average and the maximum, or the peak, is the same. So the ratio of the peak to the average is actually 1:1. So that is actually what they're asking us in a sort of tied up roundabout way. What is the ratio of the peak envelope power to the average power? But for what? An unmodulated carrier, steady state. And the answer is 1, because the average and the peak is exactly the same. Okay, next question, very similar. And let's deal with the question. What is the output PEP, or peak envelope power, of an unmodulated carrier if an average reading wattmeter connected to the transmitter output indicates 1060 watts? Well, they have just introduced a whole lot of additional information that is useful, but the focus of it is the fact that it's a peak envelope power that they're talking about, and it's an unmodulated carrier, so therefore it's similar to the previous question. And they're telling us about the average reading is 1060 watts. But what did they learn last class and just now from the previous question about an unmodulated carrier? The maximum is equal to the average. So if they're telling us here that the average reading is 1060 watts, and they're asking us for the maximum or the peak, because it's an unmodulated carrier and the average and the maximum is equal, the answer has to also be 1060 watts. So they have asked us for the peak. The peak is equal to the average. And what is the average? The average is 1060 watts. And that is how we end up with 1060 watts. So those two oscilloscope graphs is to visually illustrate that to us, that the maximum is the same as the average because it's continuous. Okay, next question in the question pool. What is the output peak envelope power from a transmitter if an oscilloscope measures 200 volts peak to peak across a 50 ohm dummy load connected to the transmitter output? Okay, again, a lot of extra words inside of there. So let's distill it, let's dissect it. What are they asking us? what is the peak envelope power? That is what they want to know, the peak envelope power, right? So we need a formula that involves power. What have they given us? They have given us that the measurement is 200 volts peak to peak. So therefore, they didn't give us peak, they gave us peak to peak. So our formula must use peak to peak. And what else did they give us? They told us it's a 50 ohm dummy load. So therefore, we also need a formula that has R in it. Again, we worked this as a worked example on the slide. That was a slightly more complicated worked example that we did that involved the use of two formulae to be able to get the answer. So the answer turned out to be 100 watts. Again, they have the workings here, not exactly step by step, easy to look at and follow. Some persons might be able to watch it and understand it clearly, but if there's any doubt in your mind, please look at the slides that were circulated at the beginning of the week. And also you can look at the video from last week's session. This is detailed a lot more as to how we got 100 watts by applying the relevant power formula. Last question before we go to the break. What is the output PEP from a transmitter if an oscilloscope measures 500 volts peak to peak across a 50 ohm resistive load connected to the transmitter output? Right, a very long-winded question. Again, anytime you get a question, dissect it. Let's see what they're asking you to solve, and let us see what they give us. And everything else really is useful information, but it's truly fluff. We just need to get an understanding of the question. What are they asking? What is the PEP, which is the power? So therefore, the answer is going to be in watts. We already know the unit of the answer is going to be in watts because they're asking us for peak envelope power. What have they given us? So they want to find out power, but they gave us, here we go, peak to peak voltage, 500 volts peak to peak. What else did they give us? They told us 50 ohms. So again, we need to use a formula that has power in it, voltage, and resistance. So we need a formula with P, V, and R. Again, we worked that out in detail in the last class, and it's on the slide deck, step by step, showed the working, and the answer was 625 watts. It's worked out here again in a very just quick way. So folks, we have just looked at all of the questions in the question pool related to all of the theory contained in the slide deck from last week's class. So at this time, let us take a 2-minute break. So you can certainly take a stretch, have some water, bathroom break, and we'll meet right back in just about 2 minutes. Okay, so welcome back, everyone. So those are some of the questions that you will encounter in the actual exams. So once you're comfortable, you should be good to go. And we will now proceed to some more slides in the slide deck on a bit more theory. Okay, so everyone should recall that during the technician level, you would have encountered the concept of the decibel or dB. And persons who would have reviewed the technician class videos would have seen during session number 3 on slide number 4, we would have dealt quite a bit of detail the concept of the decibel or the dB. So some of what we are doing here is repeated. So sometimes, instead of looking at an actual value of something, we want to compare two values to find out, how does one compare to the other? What's the ratio between them? Is one higher or lower than the other? Is one how many times the other, and so on? One value is twice times, one value is 10 times. So for example, if your first value is 1 and your next value is 2, you can say, well, the second value is twice the first one. But you could also make that claim if your first value is 50 and your other value is 100. The second value is also twice times. The same claim you can make if your first value is 1,000 and your second value is 2,000. You can say your second value is twice the first value. Notice that 1 and 2 and 10 and 20 and 1,000 and 2,000, those are quite different values. But in both cases, all three cases, we could say the second value was twice the first value. Interesting. So sometimes we use the decibel to show that relationship, especially when we are dealing with power levels. So an example, imagine you have a transceiver or radio and you're connecting it to an antenna, but in between the antenna and the radio, you have an amplifier. Why do you have an amplifier? Because your radio, the power output of the radio is at some value and you want to have more power going to the antenna, because as a ham, as an amateur radio operator with a license, you're allowed to run a certain amount of power on each of these bands. So maybe your radio doesn't give all of that power and you want to use an amplifier to output a higher power. But to simplify it, we are using a 1 watt input from your radio to this amplifier. And this amplifier is going to give us 2 watts out. So that is a twice times value. It is also an increase in 1 watt. It goes from 1 watt to 2 watts. But in terms of decibel, we can say we have a gain of 3 dB. How did we get 3 dB? This is how we got 3 dB. So the input power to the amplifier is 1 watt. And our output power is 2 watts. So the formula that we use, that we learned at the technician level, and we are reviewing again here at the general class, is that the decibel is equal to 10 multiplied by the log of the power 2 over the power 1. And we are using base 10 logs, right? So when we say log with the little subscript 10, that means log to the base 10. So your calculator will have log to the base 10. It will also have natural logs, which is ln, but you are looking at log, log, and that usually means log to the base 10. So if you're using a calculator, you're looking for the button that says log, log. So this is the formula for calculating the decibel between one power and the other. So we are using that formula here. dB is equal to 10 multiplied by the log of power 2 over power 1. So we have to calculate power 2 over power 1 first, take the log of it, and then multiply it by 10. You could look at it, you could think of it that way. So if our first power, input power, was 1 watt and our output power is 2 watts, so we're increasing the power as we go through the amplifier. But we want to know what gain that is. We said earlier, we claimed it was 3 dB, but how did we get 3 dB? Well, we plug the values of 1 and 2 into the formula. So we have here dB is equal to 10 multiplied by the log. This should be base 10, right? So again, this is what I meant by this software that I'm using somehow takes the subscript and puts it back. So this is log to the base 10, 2 over 1. So what we do is 2 over 1 is 2. So we take the log of 2, and the log of 2 is actually 0.301, and we multiply it by 10. When you multiply 10 by 0.301, you get approximately 3. So that is how we come up to the conclusion that when we increase the power from 1 watt to 2 watts, which is twice times the power, the gain is 3 dB. An interesting point to note, if this were 100 watts in and 200 watts out, guess what? This answer would have been the same 3. Because why? It is still the same twice times. So twice times something is always 3 dB gain. So let's look at it in terms of a loss. So we have been looking at a gain, an increase in power. But what if we reduce the power? Let's try that. So in this example, our input power is 1 watt, and we have an attenuation. The signal is being reduced to 1 watt. So we go in with 2 watts, but we come out with 1 watt. So we lose in. So that's a loss. Hence the arrow is pointing down, right? But what is the dB calculation? The power is halved, right? But in terms of dB, let's see what the result will be. So again, it's power 1 and power 2. So the power 2 is on the numerator, power 1 is on the denominator. So we plug them in. Again, remember this is log to the base 10, not log multiplied by 10. Again, apologies, not sure why the software is doing that. So 1 over 2, right, is a half, 0.5, and the log of 0.5, guess what, is also 0.301, but negative or minus 0.301. So what we end up with here is dB is equal to 10 multiplied by minus 0.301. So we end up with dB is equal to 3, yes, but minus 3. So notice when we double in the power, we say it's 3 dB gain. But when we halving the power, we say it's minus 3 dB loss. So notice the interesting relationship using the decibel to show ratios of power. Let's do a worked example. Again, these are actual questions in the question pool, and we will deal with these questions at our next class. So the question is, what percentage loss of power or percentage loss of power loss would result from a loss of 1 dB? So you have a 1 dB loss, but we want to know what percentage of power is lost if you say you have a 1 dB loss. So what we do, we use the same formula that we used before, that is dB is equal to 10 log to the base 10 P2 over P1, power 2 over power 1. And we plug in the values that we know. And we use algebraic manipulation, and we end up with P2 over P1 on this side is equal to this result. When we work that out, we get P2 over P1 is equal to 10 to the minus power of 0.1. That is equal to 0.794. If you use your calculator and use the exponent powers and so on, you will get this value. We wouldn't go into the actual detail of calculation. If you wish, convince yourself that this is true, but these are the workings. You plug it into the formula, you do transposition or algebraic manipulation, and you solve for the power ratio. And you get that it's 0.794, which means that it's a 79.4% power that's remaining. And if you take 79.4 away from 100%, you get 20.6 as the loss. So that's how we get that here. Again, you feel free to work through this on your own time to convince yourself that this is the correct answer. But this is how it's done, the step by step, okay? All right, so we now move on to another topic, resistors. Now, we dealt with resistors in the technician class, but now we are going to look at a couple of formulae involving when you have more than one resistor, how do you calculate the total resistance? And we have the concept of resistors connected in series. Very soon, we will see another concept of resistors connected in parallel, but we're dealing with series resistors at the moment. So when we connect resistors in series, and if we look at the diagram here, you will see a resistor connected directly to another resistor, connected directly to another resistor, or what we could say daisy chaining in this way. This is considered a series circuit, or the resistors are connected in series. The total resistance is the sum or you add the individual resistances to get the total resistance. Pretty straightforward, really. Very, very simple for series resistance. You just simply add them. And that's what the first point is saying. The total resistance is the sum of the individual resistances. Note that when you add more resistors in series, your resistance will increase. Your total resistance goes up when you are in series. So if I put a R4 here, it will increase the resistance. R5, it will increase the resistance. And the formula will look something like R, or R total, is equal to resistance 1 in ohms plus the resistance 2 in ohms plus resistance 3 in ohms, and so on, for how many ever resistors we have. Once they're connected this way, we say that they're connected in series. And when we add more resistors, to find out the total resistance of the circuit, we simply add or sum the values of the individual resistances, R1 plus R2 plus R3 plus R4. Well, like everything else, let's do a worked example. All right, so sorry for the little jumble here, but let's deal with it. So the question is, and this is an actual question in the question pool. As you have probably discovered now, all of our work examples are taken from questions in the question pool. So when we do the questions in the slide deck, when it comes to the question pool, that's why we run through very quickly in the question pool, because we have already worked out how to solve the problem here. The question is, if 3 equal value resistors in series produce a total resistance of 450 ohms, what is the value of each resistor? Well, they're just asking us a kind of roundabout question, right? They give us what the total is, and they want to know if they are all equal, what is the value of each resistor? So this is a representation of the circuit here. You see R1, R2, R3. R1 happens to be equal to R2, happens to be equal to R3. They are all equal resistors. The question told us that. And it also told us in the question that they're in series. They didn't say parallel, they say series. And this is, we know, this is how you connect resistors in series. And we know that the total is the sum of the individual. So if all of them are in fact equal, and the total is 450, we come up with the formula, the R total is equal to R1 plus R2 plus R3. But we know R is equal to R1 is equal to R2 is equal to R3. So we have one resistor value here, whatever that value is. So we represent that one value as R. So we say the total R is equal to 3 multiplied by the individual R. It's the same. So we are trying to solve the problem for R, but we have R total and we know it's 3 resistors. So we transpose using algebraic manipulation and we get R is equal to the total R over 3. But remember, they gave us in the question what the total R was. They said that the total resistance was 450 ohms. So we plug that into the formula. So we end up with R is equal to 450 divided by 3, which is equal to 150 ohms. And let's check it back. Let's work it back. If R1 is 150, R2 is 150, R3 is 150. If we add 150 plus 150, that's 300. 300 plus another 150, that is 450. So therefore, we have just verified that we have come to the correct answer by saying that each resistor is 150 ohms, because they told us it's total 450 for all, and they're equal. And we know that in series, the total resistance is the sum of the individual resistances. And we use that to our advantage and we calculate what the single resistor value is. Okay, so we dealt with resistors in series, but we now come to the concept of resistors in parallel. We are connecting them in a different way. So let us look back at what a series resistor looks like. Series, one connected to the next, but we are dealing with parallel now. Notice with parallel resistors, they are actually, well, parallel to each other. They are not in series, they are parallel. So look at them. Notice how it looks. These are parallel resistors connected. So notice when we were in series, we said when you add the resistors together, they added up and they increased as you added more resistors and resistors. to the circuit, but it's different in parallel. The first point, when you add more resistors in parallel, it will decrease the total resistance. Yeah, so it's the opposite of the series. When you connect the resistors in parallel, the total resistance becomes lower. Again, opposite to what we saw in the series circuits. And like the series circuit, we also have a formula for calculating the total resistance when you have more than one resistor in a circuit in parallel. This is our formula. It looks a little bit cryptic, but we will deal with it. It simply means that the total R, resistance total, is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus, if there was a fourth one, it'll be 1 over R4. If it was a fifth one, plus 1 over R5. So again, R, the total resistance, is equal to 1 all over 1 over R1 plus 1 over R2 plus 1 over R3. So whatever R1 value is in ohms, we plug it in. Whatever R2 value is in ohms, we plug it in. And so on, and we work it out. Don't worry, we will deal with an example. There's a nice little rule of thumb to note that when all of the resistors that are in parallel are equal, so if R1 is equal to R2 is equal to R3 is equal to R4, there's one resistance value that you're dealing with. They're all equal. You can simply divide the value of one of the resistors by how many of the resistors you have. So that's why we have this little notation here. So I put it to say that the total R is equal to one of the resistors, because they're all equal, over how many. If you have 4 resistors, you put 4. If it's 3 resistors, you put 3. If it's 10 resistors, you put 10, and so on. So this is a little quick way, if and only if all of the resistors are equal value. So we did promise a worked example, or a couple of worked examples. So the first one uses the second formula that I showed you there, which is, what is the total resistance of 3 100 ohm resistors in parallel? So what they told us is that we have 3 resistors in parallel. So if we were to look at the circuit diagram here, resistor 1, resistor 2, resistor 3, they are in parallel. And they have also told us that the 3 of them are 100 ohm resistors, meaning that they are all equal. That should light up a little bulb. We have a formula for that, yes? So this is 100 ohms, R2 is 100 ohms, R3 is 100 ohms. They are all 100 ohms. And we want to find out what's the total resistance. We can't just add them together. Nope, because they are in parallel. If they were in series, we could have added them, but they are in parallel. So we have to use a different formula. And because they're equal, we could use the short formula. Take the value of one of the resistors and divide it by the total number of resistors. That's the formula here. What's the value of each resistor? 100 ohms. So we put that into R1. What is the number of resistors we have? We have 1, 2, 3. They gave us that in the question. There are 3 resistors, so we put 3. What is 100 divided by 3? Approximately 33.3. What? Ohms, because ohm is the unit of resistance. Next worked example. Right, so this uses the longer formula. The question is, what is the total resistance of a 10 ohm, a 20 ohm, and a 50 ohm resistor connected in parallel? So let's dissect this question a little bit. So we can't use the formula that we just used in the previous question. Why? Because the resistors are not equal. We are dealing with a parallel circuit. Resistor 1, resistor 2, and resistor 3 in parallel. So therefore, we have to use a formula for parallel resistors. But they again are not equal. So we have to use this long-winded formula. R is equal to 1 all over 1 over R1 plus 1 over R2 plus 1 over R3. So what do? We plug R1 in, we plug R2 in, and we plug R3 in. But what is R1, R2, and R3? Those are the resistors, the value of the individual resistors. So R1 is actually 10 ohms, R2 is actually 20 ohms, R3 is going to be 50 ohms. Those are the values that we are plugging into the formula. So we drop down now to the next stage, and we see R is equal to 1 all over 1 over 10 plus 1 over 20 plus 1 over 50. We worked that out, but I decided to use the decimal, convert it to decimal. So we end up with R is equal, the total R is equal to 1 all over 0.10 plus 0.05 plus 0.02. When you add that up at the bottom, you get R is equal to 1 over 0.17. When you divide 1 by 0.17, you get 5.9. Use your calculator if you wish to verify that I did not make an error in my own calculations, right? And I may make errors, so participants, if you see an error, please point it out to me and we will inform all of the students. So check my calculation, don't take it for granted, check it yourself, verify please. So that's how we get the answer of 5.9 ohms. And when you come to the question, in the question pool, you will see that a question that says exactly this, they will tell you, choose from one of the correct answers. The correct answer is 5.9 ohms. And you know that you don't have to remember the value once you know the concept as to the formula. How do you calculate it? If you forget it in the exam, you just pull up the formula and plug it in and use a calculator and work it out. So you don't necessarily have to only remember the answers. You can work it out. You know how we got the answer because you have been trained to know the formula, and therefore you can apply the formula when required. So we will stop there today as far as the theory, because the rest of it goes on to inductors and capacitors in series and parallel and so on. And I would just like to indicate that most persons have told us that they have gone through the technician class material. Many persons have finished all 16 sessions. Participants who have not yet finished or gone through the technician class, if you find yourself saying to yourself, some of this material is not as clear, I encourage you to go through the technician class material, because what we are doing in the general class builds on our foundation in the technician class. So I'd like to encourage you, please, to check out this link, tech.ttreact.com. If you have not yet, we're still going at a fairly slow pace at the start of the general class, right? So giving you time to catch up on the technician class material. We know there are new students in the class, so giving you some time. So please, you could look at it on YouTube as well on a smart TV and get up to speed as quickly as possible. And also, each person, if you're not getting at least one email from me per week, then I don't have your correct email address. So you can send me an email. It's on the slide in the slide deck, robbie@9z4rg.com. Let me know that you're not getting email. The start of the classes, students should have also been receiving SMS text messages, reminders with the link. So if you're not receiving any communication from the instructor, please raise your hand or send an email, send a WhatsApp, and let me know. Those weekly emails will at least contain the previous week's slides, plus the link to the previous week's recording, as long as it is recorded on YouTube, as well as the date for the next class, as well as the link, including the short link, as well as the long link for Zoom, should you need it. If it's not working, the short link is not working, you can use the long link. So that email that you get will contain that. So I encourage persons, and we know everyone is busy, we like to encourage everyone to please check your email weekly to get the communication with all of that information. So everyone, please be safe out there. We are seeing a dramatic rise in cases in Trinidad and Tobago. We certainly hope that everyone continues to be safe, take all necessary precautions. We are still looking at what's happening with the La Soufrière volcano. Our friends in St. Vincent, please assist in any way that you can, wherever you are. There's lots of info on Zello on this React members channel if you're interested in finding out about that. So our next session will be Friday, the 7th of May, God's willing, at 8:30 p.m. And all the best, everyone. Take good care. Have a great weekend. Be safe. And we'll pick up next week. Thank you very much, Nikhil. Good night as well. Charlene, certainly a pleasure. You too. Enjoy the weekend. Kevin, man, all the best. Give you a buzz in a little bit. All right, Bob, thanks a lot. Best regards to you too. Jermaine, appreciate the feedback. kind feedback, appreciate it. You too as well, be safe. Okay, Adish, also got your note that you completed the sessions in the technician class. I appreciate the feedback. Very well done indeed. Have a good night as well. Okay, George, take good care. You too, be safe. All right, Gary, pleasant night. All the best. Franz, take good care, man. Thanks again. I really appreciate the encouragement. Chevron, have a good night too, man. Take good care. Will do, Franz. I will let her know that you, and certainly to you as well, please pass the greetings to the family. Okay, Tim, take good care. Tony, Anthony, blessings to you as well. All right, Jerome, you be safe also. Thanks a lot, Amanda, for the feedback. Really appreciate it. Means a lot. Take good care. Gats, you too. Appreciate the feedback. Yes, Sylvester, take good care. Congrats again, man. All right, Adrian, take care. Eustace, appreciate the feedback. Well, you're certainly welcome. Jesse, you too. Well, I noticed you got disconnected, but we will have the recording, hopefully, and you'll, I guess, could catch up there. Ramzan, take good care, man. You too. Okay, Paula, have a good night. Take care. Yes, Desi, certainly will make it available shortly after, between, let's say, by tomorrow or so. So all have a good night.